So we're inside the plant now at Serco. Behind me is a Marley cooling tower that the folks here are refurbishing. They've allowed us to come in, going to let us do the alignment on this machine. We appreciate them letting us, helping us out with this video. So we have an electric motor that's been moved from inside the tower to the outside. What we're doing is a spacer shaft alignment. A cooling tower is a common application, but there are a lot of them in industry. The difference is this: in most applications, you've got an electric motor and a coupling and a pump or a fan or a compressor or something here, and it's close coupled. In our case, we have a 3-foot spacer shaft that connects these two machines to each other. One of the great things about this is it highlights our NXA's capability to do spacer shaft alignments. It has an application specifically for spacer shafts, which we're going to use today. And I think you'll enjoy it. You'll see how much easier this makes the alignment, how much faster it makes it go, and it really is a special application that highlights the capabilities of our NXA. So what I'm doing now is I'm going ahead and mounting the laser transmitter detectors onto the shafts. One of the curious things about a cooling tower is often these are tapered hubs, which makes the laser tend to lean at an angle. With NXA it's not a problem because the M sensor has an adjusting screw where we can compensate for that lean if it does take place. So it really makes it a lot easier to get this set up. And you have to be creative with these sometimes. But certainly almost nothing is insurmountable with all the attachments and accessories we have for these lasers. So the lasers are turned on. They're snug down, they're not tight yet. So I've started my NXA up. I'm going to horizontal alignment. Before I put in any dimensions, I want to go to settings here. And what that's going to allow me to do is choose coupling. Now, I have two options here. A short coupled machine, your standard motor pump. In our case, we're going to use spacer shaft setting. We'll hit check to select that, and it's ready for us to put in our dimensions. Before we do, I've got to adjust the heads out so that the beams are sitting where they should. I'm going to move the stationary up just a bit so I'm striking the center of the target roughly, where it is hitting on the M sensor. Now you'll notice that the beam coming from M to S is low, and that's because we're set on tapers. But with this adjusting screw here, what it allows me to do is adjust that beam up, so even though it's sitting at an angle, I can set it on its target, and now I'm centered up on both laser transmitter detector targets. Most people that do alignment know that soft foot's important to get rid of and correct in the motor. But in a gearbox, it's also essential that you get rid of soft foot before you do the alignment. It won't change the alignment very much since we're going to bolt this gearbox down and it's going to be a stationary machine, but we need to check it beforehand. Right now, all the bolts are loose. This gearbox has just been stuck in place. I'm going to go around the corners of these feet and check for a soft foot. If you have a soft foot in a gearbox and you don't take care of it, what happens is when you tighten it down, you change the clearances inside this gearbox housing, and you can shorten the life of your gearbox and bearings that way. So we want to make sure we give it a check. We're just going to go around it manually and feel for any gaps underneath the feet, fill those in so that when we start, we know that we won't be twisting or torquing this gearbox up when we tighten it down. Because we're going to get it tight, and then we're finished with the gearbox. All the corrections are going to be done on the motor after that. All I'm going to do is go around and look for that. These are pretty solid back here, pretty solid, but I have a gap here and I've got to fill it in. I can get 10 thousandths under that inboard foot, even with all the bolts loose, which means it does have a soft foot and we need to take care of it before we start the alignment. So what I'm going to do is slide a 10 thousandth shim under each inboard foot of the gearbox and see if we can minimize the soft foot on this gearbox before we start. Now those are pretty snug now. Notice here I have a little bit. Right back there, not so much. So what we're going to have to do is actually add a little bit of shim under here on the inboard edge of this. Most of it's going to be taken care of right here now that these are nice and snug. The next thing we're going to do is check for the rough end actually using the beams. Since we don't have a straight edge 3.5 feet long, and if we did I wouldn't trust it, it's too hard to hold it perfectly still on such a narrow surface. We're actually going to use the beams of the NXA to check our rough end, see if we need to add a little shim under the motor before we start, or to make sure we're not base bound and maybe we need to add some shim to here to raise the gearbox up because the motor won't go down anymore. And to do that, it's a pretty cool way to do this, and I want to show you. What I've done is I've got my head, my laser transmitter detectors set up. I'm going to adjust them where they're right on the mark on both. Now, the one striking the M sensor just slightly high, so I'm going to lower it just a bit till I'm right on the mark. What I'm going to do is there's an adjusting screw on the top of this M sensor, and what it allows me to do is pitch or articulate that beam up and down since we're on tapered hubs. And I'll set this little locking nut here. So if you'll notice now, we're pretty much right on the mark with both of these lasers at 12 o'clock. So now what I'm going to do is roll it to the 6 o'clock position. Now from here, I can see that the beam coming from the motor striking the gearbox here is still very close to center. But the beam going from the gearbox back to the motor is moved down about 1/4 inch, actually up from the way we're viewing it. And what that tells me is this: the motor is sitting a little bit low, which is fine, that's what we want. Now, one of the benefits of the NXA is with these narrow, easy to fit in transmitter detectors also have a 30mm target. So I've got over 1 inch of play to use on these heads, which is a great benefit when you're doing a long span alignment. With a 10-meter range between detectors, you can do this shot over 30 feet apart. But the benefit of having a 30mm detector size is this: even on a 3.5–4 foot span like this, if it is out and even out substantially, it's still well within the measuring range of the NXA. So I can tell from where we're sitting now, it's well within measuring range for our laser, and we're ready to start with our alignment. So another thing that's a little different from your standard motor pump alignment is I've not tightened down the motor yet. Normally I would tighten it down before I take any measurements. I want to get some idea as to how much shim I need to put underneath the motor to get it up to the level I need for alignment, and also to take care of any soft foot. So what I'm going to do is put in my dimensions, and I'm actually going to take my measurements with the motor feet loose. Normally I would not do that, but in this case, this is a brand new installation. Gearbox has been refurbed, motor's refurbed, we're putting everything in new from scratch. So we don't really care about the before alignment values, we just want to get this thing aligned. So I'm going to touch here on the icon to begin putting in the measurements, and it asks me for the distance between the stationary and the movable transmitter detectors. And even though this is a long span, it needs to be just as accurate as if it were a short span alignment. So we want to try to get those within 1/8 of an inch or so. So if I measure from one to the other, that dimension is 32 9/16. So I'll put in 32.56. Here's something a little different. It asks, this is something we normally don't have on a close coupled machine. If you'll notice, it's asking me for the difference between the two couplings, because the difference is between a short coupled machine and a spacer shaft is we have two flexible elements. So we actually have two planes of power transmission, which means we have two planes we're going to align at. One on the gearbox side, one on the motor side. And if I take that measurement from center of coupling to center of coupling, it is 32 inches. The next thing it wants to know is how far it is from the center of this motor side coupling to the detector. In this case, it's really almost dead center. It's actually behind it maybe 1/4 of an inch. So I'll put in 1/4 inch. It wants to know how far it is from the M detector to the inboard motor foot. Fortunately, I wrote those down before I climbed up this ladder. That is 9 inches. And the last dimension it needs to know is how far it is between inboard and outboard motor feet. And again, I wrote that down, and it is 9.5 inches. The last thing we're going to tell it is the RPM. This tower runs full speed with an 1800 RPM motor. We don't even know how it'll be installed yet. Odds are good in this day and time it's going to be on a VFD or a variable frequency drive. But we're going to align it for its fastest speed it's anticipated to run at, which is an 1800 RPM input. That's already checked here on my NXA. So now I'm ready to begin taking my measurements. I'm going to rotate over to one side, let it stabilize just a hair, and I'll take that first measurement. Come up here somewhere around vertical. I'll take my second measurement. Fortunately, with a pin and bushing coupling like this one, backlash is normally not a big deal. If it is, you need to replace the bushings. This one's very stable, so it's not moving around. I'm going to take another measurement over here somewhere about the 3 o'clock position. So there's my 3 measurements, and here's what I know. It's very cool. I need to put 115 thousandths under the inboard end of the motor and 137 thousandths under the outboard end. See, remember I told you from looking at the beams it looked like it was about 1/8 of an inch change, and we're within about 10 thousandths of being in 1/8 of an inch. So what I'm going to do is, before I take this measurement again, I'm going to add about 100 thousandths under each of the 4 motor feet. I'm going to get rid of the soft foot while I'm on the outside of the tower. I'm going to tighten those down, and we're going to start aligning this thing. So what I'm going to do now is, just like we always do in our pre-alignment steps, I'm going to decide on a bolt tightening order as I rough this thing in before I get too far ahead of myself and forget which one is which. I'm just going to take a Sharpie and I'm going to number that 1. I'm going to go diagonally across to here. Number this one 2. We'll go down the long side here to 3 and back diagonally across to 4. And that's the order I'm going to tighten these bolts in each and every time I do this to improve my repeatability. I want to give these shims a little wiggle test just to make sure that they're all carrying there. There you go. So this foot here is not carrying its share of the load. The motor isn't touching that shim. Corner 2 is tight. So what that tells me, even though I know that these are all 100 thousandths of an inch thick, 100 mil shims, I have a soft foot right here. So I've got to fill that in before I start so that the motor doesn't change positions as I tighten and loosen it. So what I have here is a 15 mil shim, 15 thousandths of an inch thick. Fits swimmingly under there. So that tells me I've got a soft foot somewhere in the neighborhood of about 15 thousandths here. So I'm just going to put a little tension on it with a pry bar so I can slide this in, position it nicely. And now, much tighter, but still needs a couple more thousandths of an inch. I'm going to put a little tension on it with a pry bar again. You always want to wedge the thin shim between the thicker ones. Make a thin shim sandwich, as it were, so it's safer and you don't have to worry about getting cut. We'll slide those all back in. Make a neat little stack when we're finished. And now, we've done this as we should. No wiggle here. No wiggle here. No wiggle here. No wiggle here. So this motor is now carrying a similar amount of load on all 4 corners. So I know we've minimized our soft foot. Okay, so now I'm going to hit the remeasure key. Now, the benefit of not being tethered to a bunch of cables is I can do the alignment from out here. And if you'll notice from the screen, at least I think I can, so I can rotate from here with the inclinometer on there, and the indicator showing me what angle I'm turned at. Since I don't have cables, I'm not tied to the inside of the machine, I can do all the work out here where I'm actually going to be adding shims and making corrections to do the alignment anyway. So we'll take our first measurement. I'll rotate out of that, get somewhere up toward horizontal or vertical. And lastly, we'll rotate to horizontal for our third measurement. Now, all the bolts are tied in the gearbox, all the bolts are tightened in the motor. So I know these measurements are valid. And now what you can see is this. According to the NXA screen, we need to add 43 mils under the inboard feet, 59 mils under the outboard feet. Notice we're very close here. Both angles are in orange, and just so you'll know, this angle is the angle of the coupling closest to the gearbox. This angle is the coupling closest to the motor. So this is an angle-angle alignment. Both are under 1/1000th of an inch per inch of angularity, so they're pretty darn close. Well, we can do a little better. So what we're going to do is we'll loosen the feet back up, add shims under these. We'll go live with it in horizontal, make that horizontal correction, and we can put this one to bed. We'll be finished with it. We'll loosen all these back up because we need to add a little shim underneath it. So while I got the wrenches in my hands, I might as well get all 4 of them loose. And we're going to need to add just a wee bit of shim. So now I'm going to add the shims that I need to do the vertical corrections on this motor. I'm going to add 59 mils to each of the outboard feet, 43 mils to each of the inboard feet. 60 and 60, that ought to be pretty darn close. We're going to put in the shim values it calls for, which we just did. Now we're going to go live with it. Now I've positioned it inside with a dial indicator magnetic base to use as a stop, as a steady rest. So another feature the NXA has is OmniView. With the built-in gyros on both the transmitter detectors and on the display unit, I can orient this to the way I'm viewing it. As I see this screen now, it has the motor where the gearbox should be and the gearbox where the motor should be. So if I go into settings, I can position it using OmniView to where the screen flips, and now my motor is here on the left of the screen as how I'm viewing it. Gearbox is further away. I can turn on the gyros, and now as I look at the screen live, even though I change position on it from one side to the other, the view is always the way I'm seeing it relative to the machine. So now, with a little bit of beating and banging, we have an angularity on the motor side coupling of 0. We have an angularity of the gearbox side coupling at 4/10,000ths of an inch, or 0.4 mils. So our side to side is well within spec. So now what I'm going to do is start tightening the motor feet back down, and we should be ready to go. We'll spin it one more time and see if we're finished up. So let's see how good we did with this. We added our shims to make our final vertical correction. We did a little tapping with a dead blow hammer to get our horizontal in, and we think we're pretty close, but the only way to know for sure is we're going to remeasure one more time. So let's do that now. I'll hit the remeasure key. I can leave my stop set into place in there. I just need to remember. Notice very cool that since now we're in OmniView, the screen positions itself in the same orientation as our motor. So now motor is on my left now, gearbox is on my right. I'm just going to reach back here and rotate this shaft back around. Try to take my measurements in the same position each time. Notice if I see here on the screen, I don't have to actually see the shaft inside, since I have this animation that shows me the position of the sensors inside. So I've rolled around, which would be my 9 o'clock, and I'm going to take my first measurement. I'm going to rotate up again, watching the screen to tell me what the position of my sensors is. When I get it up somewhere close to 12 o'clock, doesn't have to be, but I'm old school and I just learned it in clock positions. That's where I turn it to. I just need to take a second measurement. And lastly, I'm going to bring it back around over here somewhere in the neighborhood of 3 o'clock. Now I don't want to slam that dial indicator mag base that I'm using as a stop. And I know it's sitting very close to horizontal. So I'm just going to kind of gingerly let it, by feel, coast back down, take my hands off of it. So now I know I'm fairly close. I'll take my third measurement. And we have a freakishly good alignment. Our vertical angularity on the motor side is 1/10,000th of an inch. Our vertical angularity on the gearbox side, 1/10,000th of an inch. Horizontal angularity on the motor side, 2/10,000ths. Horizontal angularity on the gearbox side, 4/10,000ths. So in essence, one move, one set of measurements, one round of tightening and loosening once we got our pre-alignment steps done. Using the vertical method, very important. With this laser, we don't have to measure and move and measure and move and measure and move over and over ad nauseum. We can just take one good set of measurements, put everything where it's supposed to go, and be finished with it. There's absolutely nothing wrong with that alignment. All our couplings are green, which indicate to me that everything's in tolerance. And in essence, one spin, everything's finished. So let's recap what we did. We performed an alignment using the spacer shaft function on our fixture laser NXA on this Marley cooling tower. Total time from start to finish is about 35 minutes actual alignment time. Things that make this thing special: OmniView, which allowed us to view it from either side we were working from. 30mm detectors, which meant regardless of the distance within reason, we had both the range, since it has a 10-meter range between sensors, 30mm target size. Made the alignment very easy. We did take all the pre-alignment steps, as we always do. We get rid of the soft foot, we tighten the bolts down the same each time, and by doing that we increase our repeatability, and we actually made this a one-shot alignment that we got to less than a half a mil with one spin. So I just want to encourage you, if you have a spacer shaft in your facility, especially one that's giving you problems to align, there is, in my opinion, no better tool than a fixture laser NXA for performing spacer shaft alignment.